Okay, I think, madam, we can start now. Now it is 3 o'clock.
Okay.
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 Very good afternoon, all of you. This is the 9th session of our Department of Chemistry webinar series. Today we have Dr. Sindhu S. as to chair this session, and our speaker is Dr. Soney Varghese, Associate Professor, School of Material Science and Engineering, NIT, Calicut. So let me introduce our chair first. This session is session will chair by Dr. Sindhu S. He is working as an assistant professor and head of the department of Nano Science and Technology, University of Calicut, Kerala. She did her PhD in physics at Cochin University of Science and Technology. There's a very long experience in research and academics. She was a research associate at IIT Bombay and a postdoctoral fellow at National University of Singapore. She worked as an assistant professor at Nano Science Center of Amrita Vishwa Vidyapitham University, and after that she joined in University of Calicut. She has a large number of sponsored projects, and she produced advised six PhD, and now 4 students are working under her. She has more than 50 research publications in peer-reviewed journals, and she is a member of many committees in under University of Calicut, especially the chairman POS Nano Science and Technology University of Calicut, chairman Board of Examiner Nano Science and Technology. Madam, with great pleasure, I invite you to this session, and also please chair this session. So over to Dr. Sindhu, please.
Thank you, Dr. Sujit. I think I am audible to all.
Yes.
Good afternoon to all. Dr. Soney, good afternoon. Yes.
Good afternoon.
Yes, yeah. First of all, I appreciate and I congratulate Department of Chemistry for organizing such a wonderful webinar series. And this is a session 9, means it's a continuous process. I think there are sessions coming after this also. It's a very good effort. I appreciate the head of the department, Dr. Sujit, as well as all the faculty members in Department of Chemistry for organizing this program, and I thank Dr. Sujit for inviting me to chair this program, especially my friend Dr. Soney Varghese is presenting, and there's a very interesting topic he is going to talk, and those who are attending this talk, I don't know actually, but these are all students, or how is the audience, Dr. Sujit?
So audience, PhD scholars and PG students.
PG students, okay. I think you'll get a lot of information on an interesting topic like liquid crystal materials for information display. So my job is to introduce Dr. Soney, and will hand over the session to him. Before that, I'll briefly introduce him about his achievements and background. He's an associate professor in the School of Material Science and Engineering, NIT Calicut. He is working there since 2006. He obtained his PhD from Eindhoven University of Technology. He was an MTech polymer technology student of QSAT. Before that, he did his MSc from SH College, Kochi. And he is having 65 international peer-reviewed publications, and his research area includes nanomaterials for sensors, liquid crystal display, nano and polymer technology, ferroelectrics, and nanocomposites. He produced 10 PhDs. He is the member of National Society for Optical Engineering and Society of Information Display, International Liquid Crystal Society, and currently he is the Secretary of Society of Polymer Science India, Calicut chapter. With this very brief introduction, I invite Dr. Soney to deliver the talk. I'm handing over the session to Dr. Soney. Sir, please.
Yeah, am I audible?
Yes.
Yes, sir. Yes.
Yeah. Yeah, thank you, Dr. Sujit, for inviting me for this talk. And also thank you, Dr. Sindhu, for introducing me. So today our discussion will be on materials for information display, right? So we have a variety of display systems are available nowadays. We will today we'll just discuss a little bit on what are the different type of display systems, what are the materials used, and also we will just go through a little bit on liquid crystal based display systems also, right? So to start with, as you know, the display systems, a variety of display systems are available around us, and you can see that without a display system, right, or we call it as information display systems, right, we cannot live nowadays, right? Especially you can see that after this pandemic, online classes, we are completely depending on information display systems, right? So it's basically a human machine interface, right? So starting from laptops to a smartphone to televisions or some cameras, we can find one common display item. So that is nothing but a liquid crystal display. Nowadays we have a organic light emitting diode based display systems. So these are two common display systems: LED based, all LED based, or liquid crystal based displays, right? So most of our televisions, most probably it will be a liquid crystal based, or your laptop will be mostly a liquid crystal based display systems, right? But mobile phones nowadays, you can see that there are a lot of improvement in technologies, and they have introduced the organic light emitting diodes based active matrix organic light emitting diode based display systems are also available nowadays. So a lot of research interest is going on, a lot of investment, a lot of industries are working by using this type of huge business. The display business is a huge business, right? And you can see that there are a lot of product. As I told you, we have mobile phones to LCD televisions to automotive instrumentations, small PDS, digital signatures. So one of the common thing will be our LCD, right? So you can see that there are many different type of display systems are available, right? So you can see this is our conventional CRT tube. So that is also coming under this information display, even though nowadays it is almost disappeared, right? Because of a lot of difficulties with the handling bulky sized CRTs, and it's almost replaced with the liquid crystal display, right? LCD televisions are very common nowadays. So future, maybe at some point, even LCD may be replaced. We don't know, maybe there are a lot of new technologies are also coming out. I'll just give you a brief idea about that also at the end of the session, right? Then we have plasma displays, we have organic light emitting diode based displays, electrophoretic displays, field emission displays. So these are some of the display items available in the market. So our focus will be on liquid crystal based displays. So we will just give you a brief idea about different materials, different working principles, and different configurations. What is the optics behind display? So those points, what is the physics behind, what is the chemistry behind, what is the technology behind this display system. So these points we'll try to address, right? So you can see that there are a lot of advantages if you compare with all the bulk CRTs, right? You can see that it's lightweight, low power consumption, portability, aesthetic, right? So you can see it's easily portable. right? So the other one is literally bulky, and moreover, the energy efficiency is also less, right? So you can see that the transition from CRT to LCD, you can see that this is the LCD CRT replacement era. So that was around 1995 to 2010. Most of the televisions based on CRTs are replaced with flat panel displays, and you can see that there are a lot of innovations to take place on liquid crystal based displays, especially the big screens, flat screens, etc. And you can see that after 2015, there are a lot of improvement. We have high resolution displays, right? Ultra high resolution displays, quantum dot displays, LED with organic light emitting diode based displays, holographic displays. So a lot of improvements were taking place day by day, right? And this is just showing a projected market for the flat panel display market, and you can see that. So there's a huge market. So you can see the year versus the market in $1 billion. You can see that the transparent, flexible, transparent, non-flexible, flexible, non-transparent. So different displays. So it's a huge market for all these type of products, right? And moreover, you can see that there is a lot of improvement taking place in this type of televisions. 3D televisions are available. High resolution displays, 4K, 8K. So such displays are also available, having very wide viewing angle, right? And smart tablets and smartphones also having this type of displays. And nowadays we have smart Android televisions, right? So direct internet connection, everything to the televisions using Android televisions. So these are all based on this flat panel display. And if you just look at the cost structure of a liquid crystal display, so you can see that. So this is the, you can see overall the cost of the different parts of a display system. And you can see that you have a different parts. So basically, if you just look at the liquid crystal, we can see that around 2 to 3% is for the liquid crystals, right? So you can see that. So that's quite a good amount, right? Around 2 to 3%. Other than that, you have all other components, polarizers, different drivers, backlighting systems, and printed circuit boards, electronics. Right. So I would say this is one of the very wonderful product. So which uses different disciplines, right? Different disciplines working together to achieve this product. The idea is that liquid crystals are small molecules, so the chemist has to do some synthesis to synthesize to produce such molecules, and also a physics guy is required to understand the optics behind the polarization and the wave guiding of the display system, and electronics or electronic guide will be required to introduce a transistor to drive this each pixels. So maybe a structure has to be built, and a mechanical engineer or electrical engineer will be required for the rest of the parts. So you can see that it's truly interdisciplinary, and there's a lot of interesting thing you can do in this area, right? So we are also doing some research in this liquid crystal based systems, right? And you can see this is just an overall idea about LCD area demand by application. So this is given in square kilometers. So this is the area requirement worldwide, right? So you can see that mobile phone, mobile PCs, desktop monitors, LCD televisions, etc. And you can see that 64% is based for the televisions for entertainment. Right, so consumer electronics. So you can see that. So in 2017, statistics shows that it is around 179 square kilometer. So it's a huge number, right? So because you can see that in a home, you can have more than one laptop, and everybody will have at least 2 mobile phones. And there is a television. So if you take in a home itself, you can find at least a good amount of LCD screen, right? You can find in a home itself. So if you just think globally, it's a huge market, and this is projected, and you can see that day by day it is increasing, right? So the entertainment never ends, right? So the requirement of such display systems are also demanding day by day. So you can see that this is a 36-inch television screen, right? So increasing area requires more LC material. For example, a 36-inch TV, if you want to add 1 inch, so you have to add 6% more liquid crystal. Okay. So that is just giving you an idea about the importance of liquid crystal in the systems, right? And moreover, and you can see that there is a lot of improvements, right, over the past. You can see that a lot of improvements, especially you can see the display response time. You can see that earlier days, 2005 and all, the response time was around 15 milliseconds. Nowadays, you can see 2013 between 1 millisecond, and nowadays you can see less than 1 millisecond. So you can switch very fast, right? That means if your liquid crystal is not switching fast, that means you cannot see a movie, right? So the switching speed is completely related to how well you can watch a video, right? So nowadays it's less than 1 millisecond, right? So the switching is actually a property of a liquid crystal. So it is a role of a chemist to design a molecule that can switch very fast, right? So from that synthesis point of view onwards, people have to think to achieve a high-end product, right? So it's the responsibility of a chemist to design a particular molecule for having a very good response time, right? And also you can see the thickness. The thickness, you can see that nowadays it's becoming slim. Thickness is around 0.8 centimeters or so, right? And these are also with the LED backlighting. Earlier days, we are using cold cathode, cold fluorescent lamps. Cold cathode fluorescent lamps. That is CFL. Fluorescent lamps were used, so that is giving you a little bit bulky size. But since then we are using LEDs, you can see that the display systems become more thinner, right? So most of the LCD televisions we use LED backlighting. Because of that, they say LED television, right? But it is actually not a LED television, LCD television. LED is the function of LED is to give a, so that I will show you. And moreover, you can see the display diameter, and it is also increasing. You can have it. And also the contrast ratio is also huge nowadays. You can see that the contrast, that means the ratio between the and the dark area of the television screen, that is giving you the contrast ratio. You will have a beautiful images, right? So these are very important parameters. You can see that this is also a lot of synthetic is required to improve all these parameters. Contrast ratio, you can see that it is a higher light transmission. Density televisions, everything is available nowadays, right? Everything is available nowadays. You can see that this is a 13-inch pixel. So we used to express the resolution pixel per inch, so which is usually given by PPI. So you can see that this is around 13 pixel PPI. So this is 52 PPI. So we are increasing the number of pixels per inch, right? So more the number of pixels, we have more resolution, right? So that is also possible. We have 8K, that much pixels are possible nowadays. And this is just relative display surface area, and you can just comparing with the different display systems. You can see that LCDs major nowadays. It is around 93% contributions from the LCD based displays, right? And you can see this is different companies which produces their. You can see that 11-inch Soney and 15-inch and 55-inch OLED based, and you can see the price also. You can see the $4 per square inch, and the 15-inch you can see that $1.5 per square inch, right? And nowadays you can see that it less than $1 dollar per square inch. So approximately you can see that around 1,000 rupees, less than 1,000 rupees. Yeah, I think more it's becoming more cheaper, right? So this is just showing you the growth of LCD and OLED based display systems. You can see that the cost is also decreasing with the time, so it's becoming more and cheaper, and most of the cases the prop or the performance is also improved day by day, right? So this is also the forecast of annual production capacities. You can see that LCDs, this is LCDs, and this is plasma and OLEDs. So still we can see that LCD is number one until now, but there are a lot of other display systems you can expect in the future. In coming days, we can have micro LED based displays. So those displays are also promising, right? And so you can see this CRT and LCD transition we already discussed. You can see that it's almost over. Now we are not at all producing any CRT. We are only based on LCDs, right? And so this is also giving you an idea about the LCD market. LCD market, you can see that millions of units per y-axis, and you can see that it's increasing every year, right? So there is a huge demand for such display systems, right? If you look at if you just focus on LCD, crystal-based display systems, basically you can see that we have 4 different varieties, 4 different type of display systems are available, right? So you can see that twist and pneumatic. So we can say this is one of the first type of LCD, right, which is used in watches, calculators, and other all devices. And we have a super twisted devices. We have a in-plane switching LCDs. We can have vertically aligned LCDs, right? So most of the cases for flat panel televisions, we are using in-plane IPS. So it's called IPS, and we have a vertically aligned. So that is also used in most of the televisions, right? So you can just showing you an idea about different display systems and their type of display configurations. So as I told you, most of the televisions are based on either IPS or VA, vertically aligned, right? So in-plane switching or vertically aligned. These are very commonly used in most of the televisions. And I'm just showing you different materials for the display systems or the materials, right? So if you just look at a cross section of a display, so just watch this video, so you can see that what is happening, right? So please watch this video. You can see that each pixel. I will zoom on a video. You can see that you zoom in, you can see each pixel, right? So you can see that this is the basic structure. The pixels are given here, the red, green, blue, right? And if you take the cross section, it will be like this, right? So it's a sandwich structure, right? So it's a sandwich structure, right? So this is what given here. Sorry. Yeah. So you can see that it is something like this. So you can see that. So we have a backlight here. This is a backlight, and there is a polarizer here. So this is a polarizer. So backlight is nothing but an LED light source, right? So there's a polarizer here. You can see that, and there's a substrate. Either we can use a glass substrate. On that we have a conductive substrate, that is indium tin oxide. It's a transparent conductive oxide film. And on that we have a polymer film that is called polyimide, or it's called alignment layer, which is responsible for the alignment of liquid crystals, right? And we have liquid crystals are standard here, right? So these are the liquid crystal molecules, and on the other side, the same thing is again you have a substrate having polyimide ITON glass, followed by another, we call it as the analyzer, followed by the color filters or the colors red, green, blue. So this is the basic structure of the display, right? I think if you watch this one, yeah, this video, just watch what is happening inside a display. I hope you can see
Hello.
Sir, Soney sir.
Soney sir, some audio
Yes.
break, video raised.
Sir, this video is not moving.
Some problem with the network connection. Soney sir. അറിയില്ല സോണി സാർ ഒന്നും വരുന്നില്ല, സൗണ്ട് വരുന്നില്ല, ഓഡിയോ. Soney sir, reconnecting or?
Yes, yes. I already telephoned him. He will reconnect.
Okay.
Sujit, can you hear me?
Yes. Now you can. Now call.
Okay. Just share again.
Last time that video was not working. Okay, I think you can start from.
Okay, I'll play.
Okay.
Yeah, I'll play again. Can you see my screen?
Not now.
No. Okay, let's wait. It's not coming.
Not yet shared.
Just a minute. I'll just join again.
Yes, sir.
So just
Yes. So sound is breaking.
I can see now, right?
We can see, but there's a dark. It's completely dark.
Yeah,
That's
that's
correct.
dark.
I'll play
It's a
the video.
video.
That is
Video.
correct.
Okay.
Yeah. I'll play again. Can you see the play?
Fine.
Video?
Yes. Yes.
Oh, thank you.
Sir, this video is not running actually.
Oh.
Sir, this video is not running. Simply it is.
I'll just. It's coming.
No, sir. It is not. It is not running actually.
See? Can you see?
some problem with the audio, Soney sir.
Can you see the
Audio
slides?
Still that video is showing in my screen. I can see that video, freezed video. It's not
No,
moving.
it's not running video.
Audio, okay. I have stopped the video. I'm just Can you see the slides now?
Okay, slides are there. Okay, now it's okay.
Can you see the slide?
Sir, your voice is breaking. We can see the slides.
Now slides are okay.
You can see this. Not I'm just voice is breaking.
So it's our audio breaking actually. Okay.
Slides are okay. Can you hear me now?
Now it's okay. So you can.
Can you hear me now?
Yes, okay.
Now it's okay. Okay, yeah. Now it's okay, right? Yeah. Just, so I was trying to explain the working. After that, we will move to some material side. So you can see that this is the cross section what we are talking about, and you can see this polarizers are here. So this is the polarizing. So basically, we are using polarized light. So whatever light is coming from your laptop screen is a polarized light, right? So if you just keep another polarizer, you can see the polarization of the light, and you can see that we have the indium tin oxide film, we have the liquid crystals in between, we have again the indium tin oxide, and we have an orientation film. Orientation film is actually helping you the align the molecules, liquid crystal molecules on the surface, and you have a glass substrate and again a polarizer. So this we already discussed, and you can see here another animation. I hope you will be able to see it. Can you see this this Explorer window? Can you see this?
Yes, it is working. No problem.
Okay, yeah. So just to show you the same thing, you can see how light is passing through the display system. And as I told you, we have a backlight which is LED, and the light is actually passing through the polarizer where the light is plain polarized, right? So the polarized light is actually passing through the liquid crystal material, right? And you can see that the liquid crystal molecules are aligned like this, right? So even the liquid crystal molecules have a property of wave guiding, right? So the polarized light can be guided by the liquid crystal molecules, right? Suppose you just see here what is happening. You can see that we have a light coming, and we have a red, green, and blue. 3 pixels, subpixels. So approximate size of this pixel will be around 300 micrometers, right? So we can independently switch each pixels. So we have a thin film transistor, a TFT. Probably you have part of TFT monitor. So we have a thin film transistor here. So that is actually driving each subpixel. So each color is a subpixel of a pixel, right? So we can independently control the voltage applied to the subpixel, right? For example, if I'm just applying a voltage to the green pixel, and you can see that what is happening. So the light will rotate, light will be guided. You can see that liquid crystal has changed the orientation and apply electric field, right? So you can see that light also will be twisted. So this is how the light is twisted. This twisted light will come out because the second polarizer is placed 90 degree to the first polarizer, right? So because of that, light will be transmitted, and you will see green color in your screen, right? Suppose if you apply voltage to the red pixel, you can see that the red will also be twisted, and the red light will come. So it's a combination of red and green leads to yellow color, right? Similarly, if you switch on the blue also, you can expect the white color, right? So you can see this how it works, and you can see that we are applying a voltage between 1.5 to 5.4, right? So 1.5 is a threshold voltage and 5.4 is a saturation voltage, right? So, for example, in between you can apply different voltages. For example, if I apply voltage here, right, so you can have a different color, right? So because you have a light shade, right, or if you put it here, so like that you can have millions of colors can be produced. Millions of colors can be produced just by changing the voltage, right? So each pixel voltage independently can drive by a TFT, right? So that's why it's called TFT LCD, right? So this is how it works, right? So this is what shown here, right, in the slide also, right? And this is what is called a twisted nematic, right? So we have a twist in the liquid crystal medium. So you can see that this is a twist. This is a 90-degree twist, right? The twist is given because light has to pass through the second polarizer. So we are twisting and untwisting, right? By applying electric field, right? So the purpose of electric field is to control the twisting. So on or off, either light has to come out or not. So basically speaking, the liquid crystal will act as a light valve, right? So it's a light valve, something like a tap. You open, the water will come and stop the water in between. So like that, the liquid crystal molecule is acting as a light valve, right? So you can just whatever the light you want, you can control, right? Different intensity or whatever way you can control applying a voltage, right? So that is the twisted nematic, right? Similarly, you can have you can see here. I hope you can see this animation. So this is twisted nematic. So when you are applying a voltage, the molecules are changing its orientation, and that will allow the light to pass through, right? So similarly, you can have a super twisted nematic also, and you can see that twist angle is more than 90 degree. So it can go up to 180 or 270 depending on your application. So you can have a different type of display system. So this is called twisted nematic. Then you have another configuration. So that is called parallel aligned cells. So here the molecules are aligned parallel and they will twist in between. So this is the in-plane switching system, and so this is commonly used in our televisions. So you can see this is the in-plane. You can see that electrode is only on one plane or one side of the system. Right. Other side is free. So this is the in-plane switching mode. Then you can have vertically aligned. So that is also used in televisions. So you can see that molecules are aligned vertically, right? And when you apply electric field, so the molecule will change its position, right? So in a laboratory scale, you can easily make a typical LCD screen or LCD cell just by a simple process. I'm just showing you how to do it. So you can see that just a fabrication of this you can consider as a single picture, right? So what you do, just take two glass plates having indium tin oxide. So ITO glasses are easily available. Then you can just coat some polymers on the substrate. So usually we coated poly. Then, so if I cure the polyimide, then we are doing a rubbing process, right? So this is called, so basically we are taking a velvet cloth. You can just rub this side where you have polymers. So during rubbing, micro grooves will be formed on the surface, right? So they are actually responsible for the alignment of molecules, right? So you take two such substrate and at a 5 micron spacer, you can just glue it. Then you can just fill the gap by capillary capillary rise. Just pour some liquid crystal at the edge, so the liquid crystal will be filled in the gap. So you will get a cell like this, right? So this is the rubbing process. You can see that rubbing of polyamides. So basically, we are introducing some grooves on the surface. So actually, which are responsible for what we call alignment. Okay. So this is so you can in laboratory scale we can make small display systems, right? So it won't work like a normal. It's like a simple something like a calculator type of display systems you can make in laboratory if we have this facilities, right? And if you just so this was just the basic idea I'm just trying to convey about the working of this display systems. Right? So a lot of research is going on in this material side. So especially the liquid material side. That's what we are going to discuss in the discuss now. So just to go to the liquid crystal material, a little bit on the liquid crystal material, I'll just give you. You can see that this is the first liquid crystal molecule which was synthesized, right, by a Austrian botanist. He is an Austrian guy, Frederick Reitzner. And you can see that this is a cholesteric structure. And you can see that the clearing point is around 145 degree and the nematic to isotropic transition was around 179 degrees. So this was first reported molecule in 1888. After that, you can see that in 1971, we have this type of small displays for calculators and other type of displays. People started using this twisted nematic type of displays, right? And you can see that from that day onwards, you see that there is a lot of requirement for liquid crystal materials. You can see that this is the production in liquid crystal material. One of the major supplier of liquid crystal material is Merck. It's a German company, Merck Ramstadt. You can see that this is a ton of liquid crystal produced year by year. And different materials are produced because tons of liquid crystals are required to meet the requirement of consumer electronics, especially for the entertainment area, right? And if you just look at the liquid crystal molecules, you can see that either it can have allotropic properties or thermotropic, right? So most of the display systems we are using thermotropic. So thermotropic means its crystalline phase are temperature dependent. If you change the temperature dependence, we change the temperature, alignment of molecules will change, and so because of that, we used to name it as thermotropic. And you can have allotropics also. So this is basically some solution-based systems which are not used in display systems, but for example, if you just take soap in water, it's allotropic liquid crystalline phase, right? So similarly, you can have hydrophilic or hydrophobic or flexible different systems are also available, right? So if you take a simple liquid crystal molecule, you can see that this is just one of the very basic example of a liquid crystal molecule, and you can see that this is basically a two biphenyls. So it's a biphenyl structure, right? So it's a cyanobiphenyl, and you can have a very tight structure also, right? So basically, you can see that there's a polarization in this molecule. So you have a negative side on the cyano side, positive side on the alkaline group, right? So basically, there is a charge separation or a polarization, a permanent polarization you can expect in such molecules. And for a physics point of view, you can see that the molecule looks like a rod shape. You can see that this is a rod shaped molecule, and there is anisotropy associated with these molecules, and you can see that the length and width is always something like 2 nanometer length, and width can be around 0.5 nanometers. And you can see that we can have different low molecular weight are also there, but in display application we are not using it. We are only using simple molecules, right? So that I will not discuss. And you can see that the liquid crystal is having some orders. So you can see that a perfectly crystalline material on the left side, and right side you have a isotropic material. Isotropic means there is no order, and in between you have liquid crystal phase. So this is the nematic phase. So just look at the order, right? So this is example of crystalline material, nematic material, isotropic. Isotropic, you can see is very clear liquid, and crystalline is having crystal structure, and you can see that a pneumatic phase, or we can call it as a mesophase. So because it's like a liquid, but at the same time, it has properties of a crystal. So that's why it's called liquid crystal. Right. So you can see that the cloudy nature shows the crystalline nature. Because of that, there's a crystalline nature, and light falls, light will be scattered, leaving a cloudy appearance. Right. And you can see these are the other phases available for liquid crystals depending on the temperatures. And you can see spectric phases, spectrum C, spectric A, and pneumatic. Right. So our applications, we are basically in the pneumatic phase. And we can have discotic phase liquid crystals also. So these are some examples of liquid crystals having discotic structure. So they are disc-like molecules. So they will stack like this, right? Then we have polymers with a rigid and semi-flexible side chains. These are also some examples of polymer liquids. So those things I will not discuss. Basically, we will follow liquid crystal molecules, right? So these are also polymer liquid phases, right? So if you just look at the properties of liquid crystals, you can see that it's basically temperature dependent, right? The temperature dependence is very important. Of the properties are very important because the order of the arrangement or the arrangement of molecules actually depends on the temperature, right? So when you buy a monitor, they used to specify the operating temperature, right? So the temperature it should be within the limit. Otherwise, the material will undergo some phase transition, and you will not be able to see, right? So, and also you can see that there are a lot of other properties related to liquid crystal molecules, and you can see that this is anisotropy or the dielectric constant. So you can see that, as I told you, the molecule is a polar molecule. One side is positive, other side is negative. So there is a permanent dipole position. So this is called positive dielectric materials. And if it is in the lengthwise longitudinal direction, you can see that this is negative dielectric materials. So what are used in display industries? For example, in plane switching applications, we are using positive dielectric materials, whereas vertically aligned display system, we are using negative dielectric materials. So it's basically whether it is positive or negative, that depends on the shape and the different functional group present on the molecule, right? And you can see that when the dielectric anisotropy, this is what happens. So when you apply electric field, you can see that the molecule will align like this. It will change the position like this. You can see that either one side you have negative, other side you have positive charges, right? And you can see that the molecule is also having a interaction with the surface, right? The surface, the type of surface it is interacting is also very important. Either it can be parallel to the surface, so we call it as planar alignment, or it can be perpendicular to the surface. We used to call it as homeotropic alignment, right? So these are the two different alignments possible. And you can see that the molecule will make an angle with the surface. So we call it as a pre-tilt angle. So these are also very important parameters for different adhesions. And you can see that many liquid crystal mixture properties and how the liquid crystal mixture property and the display property are related. For example, the liquid crystal clearing point, you see that? So that is actually telling you the operation temperature range. What is the temperature range the display can be operated? And you can see the melting point also related to the operating temperature. The birefringence is also related to the brightness, contrast ratio of your display system. Dielectric anisotropy of material is depending on brightness, contrast, angle. Elastic constant of the material. It depends on the parameter thing is response time, right? How fast your display is working, or it can switch. So that is depends on liquid crystal elastic properties or the viscosity. And you can synthesize a liquid crystal molecule, we may have to consider all these parameters, right? Then only you can have a very good liquid crystal, right? So unfortunately, a single liquid crystal may not meet all these requirements. So because of that, we used to go for a mixture of liquid crystal, right? So you can see that we used to take some 20 different molecules to have a mixture of liquid crystals which are used for display industry, right? So if you just you can see that if you just look at the structure of liquid crystals, and as chemist, I think there are a lot of contributions you can do. For example, if you just look at the structure, you can see that you have basically we have some bridge groups, some rings are there, one alkyl chain is there, some polar groups is there, right? And you can see that we can have a dielectric constant above greater than 0 or less than 0. That depends on type of polar group you are applying, right? So the design of the molecule is actually the responsibility of the chemist. Because all these parameters are very important. They are directly related to the performance of the display, right? So that's what I told you. We are using mixture of liquid crystals. So you can use different alkyl groups, terminal groups. You can see that these are some of the examples of terminal groups we are using. So you can see, and rings and bridges are here. You can see we can use either phenyl or oxyphenols or fluorine compounds. So these are acting as bridges. So each section of the molecule you have designed, right? Generally, you can have a very good molecule for a display applications. And you can see some of the common groups. So you can see that phenyl, the ring groups, linking groups are also given here. And some substituents are also given. So these are polar substituents. You can see the fluorine, chlorine, cyano groups. Usually, commonly in the crystals, we are using fluorides because of its high electronegativity. And even cyano groups are also commonly used. Right. So most of our televisions uses fluorine-based liquid crystals. Right. Then other than that, you can also try molecules like chlorine or bromine-based molecules also is possible. Right. And side chains can be. You can see that you can have either CS3 or other type of terminal alkyl groups can be used in this side chain. So that is also possible, right? So these are some examples of terminal groups. So if you look overall, it's an assembly of different groups, right? We just so the chemist has to think how to achieve such molecules. What is the strategy required to synthesize such molecules, right? Right. So you can see, and also as I told you, we are using a mixture of liquid crystals. So basically, of many reasons, because it's very difficult to meet the requirements.
The audio is breaking.
Sorry. Audio is breaking.
The audio is breaking.
Okay.
No, for us, its audio is okay. I don't know.
Okay.
So
Yeah. Then I'll continue.
Okay. It's okay, I think so.
Okay. Okay. Shall I continue, Sujit? It's okay.
Yes, sir. It's okay.
Yeah. So basically, we are looking at the temperature. So basically, as I told you, we are using mixture of liquid crystals, and we are looking at the temperature where your display can operate. So basically we are looking at some eutectic temperatures where the display can be operated. So the temperature control to achieve a particular temperature range, we are using mixture of liquid crystals, right? Display performance, especially the response time of display. So because of that, you can see that we are using mixtures. So you can see that around 20 to 25 substances are here. You can see that, so these are some of examples of some liquid molecules. These are based on fluorine-based systems. We can use cyano also, but usually we are going for fluorinated compounds, and you can see this some other materials. Especially, you can see that these are the first generation materials based on this azo compounds. Azo compounds are also commonly used, right? And cyanobiphenyls are very old materials, but still in some other applications we may be using, right? So you can see cyanobiphenyls. But you can also think about cyclohexane substructure-based materials. You can see that. So these are some materials which are used in such display systems. And phenyl cyanohexanes, so these are also commonly used, right? And cyclohexanes, so these are also commonly used. right? And we are also using some chiral dopants. Basically, in super twisted pneumatic displays, we are using chiral dopants. These are some of the chiral dopants we are using. So they are responsible for increasing the twist sense from 90 degree to 180 or 270 degree twist. So these molecules are left-handed or right-handed. So they will twist the liquid crystal to that direction if you mix liquid crystal with some chiral dopants, right? And we can have the advanced liquid crystals are in the form of fluorinated molecules, and you can see this trifluorophenols, some trifluoromethoxyphenols, then difluoromethoxyphenol derivatives. So these are some of the other commonly used molecules, right? And you can see this fluorinated materials also. You can see that. So basically, the function of fluorine is basically to introduce the polarization, right? Because polarization is very important. And you can see that why we are going behind fluorinated compound is to basically to improve the mix of phase range, right? And also good voltage holding ratio and good specific resistivity, high dielectric anisotropy. And you can see that modern pneumatic phase range, lower melting point. So because of these reasons, you can see that we are basically looking for fluorinated liquid crystals, right? So people do synthesize molecule using some molecular modeling methods, right? So you can predict many of the parameters of the molecules like dielectric anisotropy, biorefrigerance, then other viscosity or viscoelastic properties, which are very, very important for a successful liquid crystal molecule, right? So we can use combinatorial chemistry, synthetic methods for synthesis, right? So because of that, I can see that liquid crystal materials are very expensive, right? So we don't have much companies is synthesized commercially, and as I told you, most of the liquid crystals are supplied by the Merck companies, right? You can see that you can have low bifringent materials. So these are some examples of low bifringent materials. This is another example, right? So I'm just showing you some structures. I can see this is difluoroethers having some bridge structures. You can see this is also difluoroethers. So these are all used in different purposes, right? And so we can have tetrahydropyranes also we are using for different applications. You can see that this is 2,3-difluorophenane compounds. These are also used in different applications. Difluorointanes we usually use for particular applications, right? So and you can see that all these properties are very important, right? You can see different technology. For each technology, we may have used different materials. VA, you can see that low rotational viscosity. You can see that IPS, TFT, twisted pneumatic, then bifringence, then projection, etc. Different material has to be used. For each and every application, you have to design a molecule, and that will be useful for a particular application, right? So that's a brief about liquid crystal, and I think I'll just skip these molecules. You can just look at some developments in the liquid crystal field. That is nothing but the quantum dot display. So I think with this we will end our discussion. So just to giving you some brief idea about quantum dot display, it's called a QD. QD displays, as you know, quantum dots are nothing but semiconductor nanoparticles, and you can see that the color depends on the size, right? So this is, you can see that different size, and the light produced. You can have different type of quantum dots, cadmium selenide, zinc selenide, then different type of materials are nowadays available, and they can give you very good colors, right? So basically, the use of quantum dots is basically to improve the purity of the color. The color purity improvement, we are using quantum dot. Other than that, basically, we do have liquid crystals using quantum dots, right? Again, but only thing, the variation is only the purity of the color you are obtaining. That means you have a vivid colors. Your images will be of high quality, right? So you can see that this is basically we have when the quantum dots are illuminated with ultraviolet light, that quantum light, see that transform from conduction band, and then when they de-excite, they emit light. So the color of the light depends on the valence, that band gap, right? So most of you are familiar with that. And you can see that as the size decreases, the valence band, the band gap, as the size of the quantum dot decreases, the band gap also increases, right? So that's what shown here. And we can see that the size dependence of color, right? So for example, you can see that these are some quantum dot colors, from the quantum dots. You can see that usually quantum dots of size 5 to 6 nanometer will emit a long wavelength, orange or red, and small quantum dots, so they will give you some blue or green range, right? So you can see. So these are some wonderful colors produced by the quantum dots, right? Because cadmium selenide and zinc selenide quantum dots, right? So these are very, very small size, 6 nanometer, always less than 10 nanometer, right? And the size dependence of color we already discussed, right? So if you just basically look at the color spectrum, and if you compare with conventional TV, LCD TV, and the quantum dot TV, you can see that the color purity will be high. So that is the basic aspect. So why we are going behind quantum dot display is basically the purity of color. So your red will be pure red, right? So like that, you have a lot of improvement using quantum dot. So just to look at this in this case, you can see that we have, this is the normal display systems. We have a light, and there are some cases when we use a phosphor material that will give you some light, and that light will be controlled using some pixels, right? So there are the color filters. But in this case, we can see that the light will fall on a quantum dot film. So this will be acting as a film, right? And the quantum dot will produce corresponding light, so that you can see that you can have 64 times more colors than our television. So it will give you high pure colors, right? And you can see that in quantum dot display, we are also again using the liquid crystals also. You can see that, so you have a liquid crystals again here. But what is the modification is that you can see we are inserting an extra film. So it's a quantum dot film, right? So that will help you to improve the color, right? And so this is a typical quantum dot display. You can see that. There are displays, so that is a film-based display. You can also think about color filters contains quantum dots. So this is a blue color filter, green color filter, and red color filter. So they contains blue, green, or red quantum dots. So they will produce that colors. Right. So you can see this is example of a different type of quantum dot based so you can see this quantum dot sheet based display. This is quantum dot glass based. This is quantum dot pixels. Right? Dot pixels each quantum dot. Right? In this case also we are liquid crystals. So in cases liquid crystals used function of to improve the color. But you can have a liquid display also possible. They're called electroluminescence. So many of field dots cannot light. In this case, you don't need any liquid crystal. So that is also under research. Quantum dots electroluminescent display. So this is what we call quantum dot electroluminescent display. So you can see that we have a Hall transport layer, electron transport layer, then we have a quantum dot material, light will be produced. Right? So we can have a perovskite based quantum dots also. So that is also used in some applications, right? So you can see some vivid colors from quantum dots, right? And if you compare different display. So we have discussed based displays. We have quantum dot display. We can also can have organic light emitting diodes, right? And we can also recently in 2019 onwards, people have started making micro LEDs. So you can see these are the available display systems. Micro LEDs are in the beginning state, maybe in 2021 or onwards, it may be available in the market. And you can see that if you compare different display systems, you can see this is the LCD, which is low cost, mature technology, and largest market share nowadays. OLED, you can see that OLED, there are commonly used in a small scale display. It's very difficult to make large scale display. And problem with OLED is that the dye molecule can degrade and the life of the display may be reduced at some point of time, right? But the future future, even though a little bit expensive, the future may be in the micro LEDs, right? Micro LEDs, which can have very good high brightness, excellent stability, high pixel density, etc. Right? But still, you can see that LCD market is also still open because of the low cost of the material. Right? So once the cost can be reduced for the micro display, so we can have it will be more profitable. And so other than that, nowadays we can have, now we enjoying LCD and quantum dots and OLEDs are nowadays available, but maybe future it may be micro LEDs. Right. So I think with this we will stop today's presentation. And if you have any questions, we can just discuss.
Thank you, Dr. Soney. Now the session is open for discussion. So you can ask questions. Anything to check? Any questions? I'll start from, I'll ask one question. I'll start the question answer session. Compared to this OLED and quantum dot display, which one will be having more lifetime?
Yeah, I think lifetime will be more for quantum dot. Because as I told you, the organic light emitting diodes, which if you look at the organic light emitting diodes, each pixel produces its own light. We don't need any liquid crystal in that case. Each pixel is having its own light source. So high contrast ratio, high high color gamut, everything you can expect for a organic light emitting LEDs or OLEDs. The problem is that the dye molecule may undergo some degradation. So if you look at the life, so if you lifespan, so most of the cases organic light emitting diodes may have a lesser lifetime compared to quantum dots, because quantum dots, most of the cases, they are inorganic materials, and also we are using liquid crystal based display system. So in such cases, the life expectancy will be more for quantum dot based. But when it comes to micro LED, they will be having much more life expectancy than, or better, or relatively better than even liquid crystal devices.
This micro LED is what kind of material? That also inorganic or organic?
Yeah, that is also inorganic only. Gallium nitride, something like that. Only thing is that these are very individual LEDs are there. Small LED, red LED, blue LED, and green LED. So they are less complex than LCD, and they have high contrast ratio. The black will be more blacker than LCDs. LCDs, problem is that the black is not perfectly black because of the crystal anisotropy. Some light leakage will be there. That leads to the poor contrast ratio. But for micro LEDs, you can have infinite contrast ratio. A huge contrast ratio you can expect.
Okay, thank you. One more thing I want to ask Soney. Like in the liquid crystal, you said in the beginning there is some rotation, in plane rotation of the molecules. What kind of experiment we can use to find out this kind of molecular characterization? Beginning, not before that.
Yeah, basically we are looking at the transmission voltage characteristic. Transmission voltage characteristic. So when you apply electric field,
yes,
and we are having a light source also, we are plotting voltage idea whether so it's basically TV, transmission voltage characteristic. So you need a power supply, AC power supply, and also you need a photo detector and some light source. So basically we can plot the transmission voltage characteristics. So that will give you some idea about how fast the molecules are switching.
Okay.
Yeah.
Okay, thank you. Some questions in the chat box. No questions.
Good afternoon, sir. I have one question. Can I ask?
Yeah, please, sir.
Sir, you mentioned so many molecules. Some of them are, containing fluorine. Some of them are containing nitrile, and even the azo dyes are also there.
Yeah.
Some of them are having cyclohexyl group and the benzene ring within the molecule.
Yeah.
I mean, you explain about the fluorine containing molecules. What are the characteristics? But I am just wondering, what is the main, component responsible for these LC molecules? So combining all the molecules, there are several kind of molecules are there. What is the main, major thing if you want to develop a molecule, a LC molecule?
Yeah.
What we need to take care?
Yeah. Basically, you can see that the shape of the molecule. The shape of the molecule should be having some anisotropy. So that is one point to be remembered, and also the polarizability of the molecule. So the molecule should have a permanent dipole. That is one aspect. So that's why we are introducing such electronegative groups into the molecule. And in between, you have that ring as a biphenyl or cyclohexane. Basically, that is to give a shape, rod shape. Because of the rod shape, the molecules have some particular alignment, right? And also we may have to think about molecules. We may have to synthesize molecules so that will be within it should be liquid in the normal ambient conditions, but at the same time should have some anisotropy. So these are the things to be remembered when you start thinking to design a molecule. Molecule should have a rod shape and it should be polarizable. Basically, these are the basic concept. And after that only we start thinking about the rotational viscosity, the response time, how they are connected to the structure of the molecule. So basic aspect is the polarizability as well as the shape of the molecule.
So in one slide you mentioned that the first molecule, which is a cholesterol type of compound.
Yeah.
Does that it is also having the all characteristic features of this?
Yeah, basically,
it looks like a rigid molecule.
Yeah. It's basically actually don't have a rod shape structure. It's actually coming under the cholesteric type of liquid crystals. Basically, what they have observed is they have observed two melting point for a material. So that's how that material were noticed. So they have observed two melting point. One corresponds to the actual melting, and second melting point corresponds to the mimetic to isotropic transition. Right. So because of that only they have noticed that molecule. Later they have developed, even though that don't have a rod shaped molecule, but it is having this type of phases, multiple phases. It's coming under cholesteric material. So which are used as dopants, doping materials, or some blue phase applications. We are using cholesteric material.
Okay. Thank you, sir. One more doubt within that question. So I'm just wondering, these molecules are, rotating the light, right, sir?
Yeah, rotating this light.
So
yes.
I am wondering, does this molecule should have a chiral center within it?
Usually, for a normal twisted nematic, we don't need a chiral.
Okay.
Because what we are trying to do for rotation is that we have a two substrate which having a very small spacing. Usually it is coming under 5 micrometer or less than 5 micrometers, and we have two substrate, and on both substrate you have a alignment layer. So one alignment is so these alignment layers are at 90 degree, right? So one is 0 degree, the bottom is aligned 90 degree to the rubbing direction of the bottom of the first one. So one is 0 degree, bottom is, it's like orthogonal, right? Like a cross. So because of that, the molecule which is on the first substrate having 0 degree will slowly progress its alignment to the top, right? But when it's aligned to the bottom substrate, and when it progresses to the top substrate, but that is 90 degree. So the top and bottom substrate molecules which are touching the substrate are at 90 degree, right? So slowly, so the molecule in the center will be something like a 45 degree, right? Because bottom is 0, top is 90. So molecule in the center of the liquid crystal will be at 45 degree. So that's how we are introducing the twist. So when the polarized light comes in, because it is polarized in one direction, it can be wave guided, right? So light has some interaction with the liquid crystal molecules, and because of that, it will follow the twist of the liquid crystal molecule, right? So that's how the twist comes in. And the chiral dopants, basically we are adding to change the twist angle. If you want 90 degree to increase 90 degree to 180 degree or 270 degree, you can need some chiral molecules. So that will further control the alignment of molecule so that the twist will go up to higher values. In such a super twisted kinematic, we are using the chiral. Otherwise, liquid crystal, we cannot say particular chiral is that important. It's not that some molecule may have, but not that important in normal cases.
Okay. Yeah. Thank you very much, sir.
Yeah, thank you, sir.
Thank you. And any questions? Dr. Sujit?
Yes, sir. Yes, ma'am.
Yeah.
I think there is no other questions.
They can type.
So any question? Okay.
If no more questions, then we can
Yes.
conclude the session, right?
Yes, we can. Okay. So, madam, you can tell something.
Yes, yeah. So, let me conclude the session. I think no more questions from the audience, those who are listening. So, let me thank the speaker, Dr. Soney, for a wonderful talk on liquid crystal materials. And I think we have touched many sides of the liquid crystal materials. And each topic will be a more than one or two or more lectures will be needed to get more information about each topic. Anyway, he covered all the areas, most of the areas related to the liquid crystal display, and I thank him for a wonderful talk. Thank you, Dr. Soney, for this wonderful talk and very informative talk. For I think the audience is very heterogeneous audience. I think they have typing their address in the chat box. So students also there, school students or school kind of.
I don't know, madam. Actually, some teachers, some school teachers, maybe they have participated.
Okay.
I think.
Okay. Then thank you, Dr. Soney.
Thank you, Sujit.
Thank you, madam, for your
thank you, Sujit.
time for us.
Connection thought. Yeah, in between the connection. Yeah.
That is not a problem, sir. I got some video you could play. That's all.
Yeah.
That's all. Okay, madam, Sindhu, madam. Thank you very much for your time. Okay. Thank you.
So next time, so you are thank you, sir.
Okay.
Thank you, sir.
See you.
So you are organizing this webinar, sir. Sorry, one thing. Webinar means every week or how
every week, madam.
Yes,
Okay. Every week.
Okay. Thank you.
Okay.
Yeah.
Thank you. See you.
Okay, then bye. Yeah.
Thank you, sir.